All right, good evening, everyone. For those of you that don't remember me, my name is Andrew Farrington. I work for SGC Engineering, and today we're going to start our lectures on transformer protection. Transformers are extremely important pieces of equipment with specific and unique protection considerations. So my goal for this class is to cover, at a high level, how do transformers work, why do we use them, what what makes them up, what are they made of, their unique electrical characteristics, most of which should be reviewed, but I want to touch on some key points. And then probably in the next lecture, we'll dive into the actual transformer protection, the differential protection, the overcurrent protection, fusing, sudden pressure relaying, other ancillary devices, and things of that nature. So this is a diagram of an ideal transformer. And so you have the high voltage system that has a source, and then you have the current flowing through a winding that is wrapped around a magnetic core, usually laminated iron. And using the right-hand rule, this current flowing through this winding creates a flux that then flows through the core and down through this winding or coil. And then because of the flux flowing through that coil, again, due to the right-hand rule, that then flows out and into load. So that's an ideal transformer. Again, I know that's review for everybody, but this is what we're talking about. This would be a single phase transformer. And the operation of the transformer has some basic characteristics, and we're going to just cover these briefly. The A is the turns ratio, which is equal to the number of turns on the high voltage winding divided by the number of turns on the low voltage winding. This is known as the turns ratio of the transformer. A is also equal to the voltage on the high side of the transformer divided by the voltage on the low side of the transformer. So these two numbers are equivalent. So if you have a transformer with one winding on the high voltage side, which I guess it would be not high and low voltage, but you understand what I mean. If you have one winding on the high voltage side, one winding on the low voltage side, the turns ratio of 1. If you put in 5 volts on the high side, you'd get out 5 volts on the low side. So those are just correlated linearly. The current in the high side is inversely related to the turns ratio. So if you have a lot of fault current or a lot of current through the high voltage winding, you'll get a related amount of current out of the low voltage winding related to the inverse of the turns ratio. So I guess the key takeaway is, if you have a high voltage winding and you're providing power to a load, the high voltage winding will tend to have a lower amount of current than the low voltage winding, which will have a higher amount of current because the voltage times the current is equal to the power transmitted through the transformer. And because of this last property, the power into one side of the transformer is basically equal to the power out of the other side of the transformer. If you have a higher voltage on one side, you have a lower current, and the inverse on the other side. And given these basic properties of the transformer, we're going to get into why do we use them. So if we go back and we have these properties of Ohm's law, where V is the voltage is equal to the current times the resistance, and power is equal to the current times the voltage, and power is also equivalent to the current squared times the resistance. It's just substituting this into that equation. We can see that for a given amount of transmitted power, as the voltage increases, the current decreases proportionally. And given that the amount of current, the resistive losses are exponentially related to the amount of power, to the losses. They're exponentially related to the amount of current going through the circuit. You can see that for a linear increase in voltage, you get an exponential decrease in losses. And so that's a pretty cool thing about transformers, and that's basically the basis of why we have a transmission and distribution system. The higher voltages are used to exponentially decrease the losses on the system. So I apologize for this. I just put together a brief example in Paint to demonstrate the point I'm trying to make. The math is kind of clunky due to time. I went through this last year, but due to time, I'm probably going to just skip over this. But if you go through the math here, we're taking a very simple case where you have an infinite source and then a line with a resistance of 10 ohms and then a load rated for 1 kV that is drawing 1 MVA of power. And if you convert all of these quantities to their per unit values and do the math, you have a current of 1 per unit going through the transmission line. And because of that 1 per unit current times the 0.01, or excuse me, divided by the 0.01 ohms, you get 1,000 per unit of R, and therefore you get low line losses of 10 MVA. So you have 10 MVA of losses in order to provide 1 MVA to the load. That's terrible. Obviously, nobody would ever do that in reality. But if we introduce some transformers that just step up the voltage from 1 kV to 10 kV and then back down from 10 to 1 kV, now the resistance, the apparent resistance of this line is decreased by a factor of 100, right? So instead of 1,000 per unit, it's 10 per unit. And we've increased the voltage by 10 times, but we've decreased the apparent impedance by 100 times. So that's that linear to exponential relationship that I'm trying to emphasize. So if you redo these calculations with the consideration of these transformers, you now see that your losses are 0.1 MVA. So instead of losing 10 MVA on the line, you lose 0.1 MVA on the line. So that makes it a lot more tenable to supply 1 MVA of load with 0.1 MVA of losses on the transmission system instead of having 1 MVA of load with 10 MVA of losses. Nobody would ever do this. That seems reasonable. Therefore, you know, this is why we use transformers. So this slide just kind of goes over all of those talking points I just discussed. So this is why Tesla defeated Edison in the War of the Currents back when electricity was newly discovered in the late 1880s. Tesla was an advocate for AC current because of being able to use transformers and being able to step up the voltage easily and transmitting it over long distances, where Edison was a proponent of DC power. There used to be old DC substations. Last year, Adam even talked about one. I don't know if he did this year or not, but apparently they're still out there, I guess. But those DC systems have basically all gone, and this is why. I did have a note in here that this example I came up with, don't try to calculate what the what the sending in voltage would be, because it's not going to be anything that's close to realistic. Again, this was just an example to try and demonstrate that that linear to exponential relationship between the voltage and the line losses. All right, what are transformers made of? The main parts of the transformer are the tank, and this is the body that surrounds the transformer, and it's typically made of steel. The core is the ferromagnetic core through which the magnetic flux flows. So back in this initial diagram, this would be the core here. Again, this is a single phase, single winding, or two winding, one winding here, one winding here, and a single phase, but that would be the core. We'll talk about two winding, three phase transformers and what the core looks like. They're a little bit different, but. And then the core is usually made of laminated iron, and the iron is laminated to reduce the amount of eddy current losses. The windings, the primary and secondary windings that are wrapped around the core, and they're typically made of insulated copper. I have seen some that were aluminum, but usually it's copper. The bushings are a hollow electrical insulator that allows the connections from the primary and secondary windings to the rest of the system, and they're typically made of porcelain, and those may or may not contain your transformer CTs. The insulation, the transformer is probably filled with mineral oil, which is for most power transformers, or it may be dry type, which is basically has no oil in it. The mineral oil, it has a couple of nice properties. One, it's used to insulate the core and the windings from the tank, because it's a better insulator than just air. It also prevents corrosion, because the air has the tendency to be able to corrode iron, cause rust or whatever, may have other contaminants in it. And it also gives the transformer some thermal inertia, right? So if you're heavily loading the transformer and the core and the windings are heating up, it's going to heat up that oil, but it's going to take a while for the oil to heat up, right? So that can transfer or disperse some of that heat from the core or the windings into the oil, and it can potentially prevent damage for the transformer. So the oil's got several really nice properties. So that's why they're very common for power transformers. The conservator tank for a lot of oil-filled transformers, you want to keep the transformer tank completely filled with oil. So you don't want any air or other contaminants getting in there. So, but the problem with that is, as you have changes in the temperature of the transformer, as load increases and decreases and the ambient temperature around the transformer changes, the oil can expand, contract. So you need to account for that. You can't just top it right off with oil and then let it go. So there are two primary ways of keeping the transformer tank completely free of air. One is a conservator tank. So the tank will actually kind of sit above the transformer, and it'll be connected via one or two pipes down to the main tank, and you'll actually overfill the transformer with oil such that some of the conservator tank is filled with oil. And then as the oil expands, it just fills up more of the conservator tank. And then as the oil cools, it settles back down. And but at no time does the inside of the transformer ever become exposed. All of that corrosion and stuff can sit up there in the conservator tank and not bother the power conducting parts of the transformer. The other option is to get rid of the conservator tank, and then you can't fill the transformer all the way up to the top of the tank like we just talked about, but what you can do is put a layer of nitrogen because it's inert and it isn't going to corrode the equipment inside the tank, and you can put positive pressure greater than 1 atmosphere um, on in a layer of nitrogen on top of the oil. And so then as the oil expands, it just kind of increases the pressure in the nitrogen, and maybe some leaks out, but you always maintain that positive pressure on the nitrogen blanket above the oil. You also have typically a no-load tap changer, also known as a de-energized tap changer, and that's a way to change the transformer ratio, typically within a range of plus or minus 5% of the high voltage rating. And the no-load or de-energized tap changer can only be changed when the transformer is not under load, thus the name. The other type of tap changer is the load tap changer, and this is also very common. And usually that will allow you to adjust the turns ratio of the transformer, typically plus or minus 10% of the low voltage rating. And this can be changed while the transformer is energized. And most often it's an automatic change. So you've got a load tap changer controller that is monitoring the voltage on the low side of the transformer and then adjusting the LTC tap position up or down in order to maintain a constant voltage at the loads. So as the load increases and you're drawing more current through the transformer and you get more of a voltage drop through the transformer, you increase that secondary voltage to maintain an appropriate voltage for the customers on the low side. So these are a couple of pictures of transformers. So this one here, these black parts, those are the bushing. So the primary connection comes down, hits the bushing, and then inside of here is hollow. And there's a conductor that goes down, and that'll tie into the windings on the high voltage side of the transformer here. This is a neutral bushing. You can see it's a little bit smaller. It's heading over here to, I don't know if that's some sort of lightning arrestor is my guess. This isn't a I just found this picture online, so I'm not entirely sure, but probably a lightning arrestor so that the high side isn't grounded. This here would be the conservator tank attached. So that's what I was saying, like you'd overfill this transformer main tank, and then somewhere, in this area, there would be a layer of oil, and then as that expands, it'll fill up more and more of this, and then as the oil contracts, it'll fill up less of it. But that'll keep that totally full of oil. Let's see, what else? Oh, yeah, another important part, I guess I didn't have that on the slide. Yeah, is radiators or fans, other cooling methods other than just the oil natural and air natural rating of the transformer. Often they have other ratings that are associated with some sort of cooling. So whether it be fans are the most common. They'll have radiators that allow the oil to circulate through there and dissipate the heat off into the atmosphere. And then you'll have fans that'll help cool down the oil. And then there's also forced oil, where they actually pump the oil around through the radiators and the fans. This is a kind of a cross-sectional view of a similar transformer to this picture, but not the same one. Inside here would be the core and the windings. Let's see, what else? So this transformer is actually up at Bingham Wind Farm. This is a 3-winding transformer. This is the high voltage side, and then this over here is actually a tertiary winding that's going over to a synchronous condenser. And then on the far side, you can't really see it, would be the high voltage side. These are those radiators I was talking about. So this is tied into the tank. So the hot oil will come in up here and then fall down through the radiators, cooling as they go, and these fans are blowing air over it to help cool it down, and then they'll come down over here, and then as they get back into the tank, the oil will heat up again and rise, and so the oil will naturally circulate through the radiators that way. These are actually more radiators here. I think there's another fan bank. Oh yeah, right there. Yeah, these fans here. I think this one had 2 stages of cooling. There are also kind of lower voltage transformers, and we'll just briefly cover those. It's not really the purpose of this class, but these are pad mount transformers. You may or may not have seen these little green boxes in cities or around larger buildings, and maybe you wondered what they were, maybe you didn't, but they're pad mount transformers. They're typically used for large industrial electrical customers or buildings. You actually probably have plenty of them on campus. Inside one compartment will be the high voltage bushings. This is showing that this has a no de-energized tap changer or no load tap changer. Then you've got the low voltage terminals on this side. This particular transformer has a thermometer, oil level gauge, and a pressure relief valve. And then this is kind of another view of the inside of one. They'll have typically a foundation that has a hole in the middle, and that'll be where the underground cables go. So these are the high voltage connections, and then these are the low voltage connections here going down into the building. And then at an even smaller scale, you've got distribution transformers, which serve small customer loads. This is what you'll see on the pole outside of your house that's feeding your house or your parents' house or whatever. They'll tap down and they'll go to the high voltage bushing. This particular transformer here is also showing an arrestor to protect from high voltage transients, and that'll be tapped. And then you've got ports here, ports connections on the low side, and those are the low voltage bushings. So you can see those here, and they've got some cables attached. And then this particular one is heading down into a conduit. Maybe it's going to feed a house underground. Also, you might see like an attachment point on this pole that it has an aerial span to the side of your house, and then the cables run down into your main panel. So inside of there is the coils and the core of the transformer, and this is usually oil filled as well. This is a different type of can. This one actually looks like it's phase to phase connected. So it's got 2 high voltage bushings. Usually you'll see they just have one high voltage bushing and then the other one goes to ground. This is an example of a transformer nameplate. And to just kind of re-emphasize all the stuff we just talked about, this transformer has an MVA rating of 10/11.2/14 MVA. Excuse me. So 10 is the base MVA rating. That's the ONAN rating, which is oil normal, air normal, or normal or natural. I guess it doesn't matter. The result is the same, right? This 11.2 is actually at the 65-degree rise. This transformer, this particular utility historically had 55° C rise rating transformers, and they've recently also included a 65° C rise rating. So that's why it's a little bit confusing, but 10 is the ONAN rating at 55° C, and then 11.2 MVA is the ONAN rating at 65° C. And then 14 MVA is the top transformer rating, which would be at 65° C, and then oil, natural, air forced. So basically a bank of fans turned on. It's a 36.2 delta to 13.2 kVY transformer, 3-phase, 60 hertz. The percent Z is not stamped on here, but you can see it gives it at the ONAN rating. And then the de-energized tap changer position voltage. Here is a table that shows the different no load tap changer positions. So it says de-energized tap changer position voltages and currents. So we'll cover what these connects means when we get to I think it's the next slide, but basically there were, for this particular transformer, 5 positions. That's pretty common. C is the neutral or rated voltage, and then you can go plus or minus 5% of that nominal rating. And then that actually changes your current rating for the transformer as well. There's also the load tap changer positions. So you can see this is the neutral position, and that's at the 13.2 kV nominal rating for the transformer. And then it has 16 positions that are raising the voltage, and 16 positions that are lowering the voltage. And this is a total of plus or minus 10% of the nominal low side voltage rating. This is again, a nameplate for that same transformer. You can see the H1, H2, and H3 bushings, and then the X1, X2, and X3 bushings. And then because the low side is a Y with the neutral available, you have the X0 bushing. Let's tap to that. And then I said we would talk about the connects term on the previous slide. What that's saying is that, like, you can connect T5 to T6 or T3 to T4, but that's which taps of those windings are connected in order to develop that no load tap changer position. So that's what that's referring to. And then this is a picture of the load tap changer, and it's obviously simplified, but basically, you know, there's a selector switch which gives you either raise or lower, and then this will just change the taps to deliver all of the different possible voltages that are available with the LTC. Of particular importance, like we talked about and we'll continue to talk about, is the vector diagram of the transformer. Pause now and see if you can remember what this vector diagram is. It is a DY1 vector diagram. So the high voltage, right, because of the H, so that's a capital D. The low voltage winding, it's a Y, so it's a lowercase y. High voltage is capital, low voltage is lowercase, right? And then if you extend this vector here, kind of over onto this delta, this is where the X1 would be, right? And the rotation of the vectors is counterclockwise, like that. And so if you have an eye over here sitting at 0 degrees and you're watching that vector rotate, the first one you'll see as this comes around is the H1, and then that will be followed by X1, 30 degrees afterwards. So if you had like a clock, right, where 0 or 12 is here, 1 would be here. These are separated by 30 degrees. So if D is at 0, which is a convention because it's the high voltage winding, Y would follow by 30 degrees and would therefore be at 1 o'clock. So this is a D Y1 transformer. So that's how you determine that based on the vector diagram if it doesn't give it to you directly. Couple things to remember about the vector diagram. It's dependent upon the system, the phase sequence of the system. Most of North America is positive sequence. That's more or less taken as a taken as an assumption. I think I've only worked with one utility that had a negative sequence rotation for their system, not like a particular transformer or whatever, but they just their whole system was negative sequence. So they had a 3-2-1 sequence for all of their stuff. So needed to certainly account for that in the relay settings I provided for them. But I've only seen that the one time. So I would, if not defined, I would assume that the system sequence is positive. So assuming that your system sequence is positive, this vector diagram is appropriate if you connect the phases in a positive sequence. So what I mean by that, I have a slide on that too, but I think it's better to show that graphically here. So if you connect this A, B, C, or 1, 2, 3, whatever the convention your particular client or utility is using. Again, if we have our eye over here watching this rotate, you're going to see A, and then B, and then C. But that really depends on where you start, right? You could also say that this would be C, and then A, and then B, or C, A, B, C. Yeah, that's right. Or which one haven't I done yet? B, C, A. So yeah, sorry, got myself turned around there. So A, B, C is positive sequence, as is B, C, A, or C, A, B. And so these are all positive. And then negative would be the opposite, right? So it's C, B, A, B, A, C, or A, C, B. Okay, so you have 3 positive sequence connections that you can potentially do, and then you have 3 negative sequence connections that you can potentially do. So if your phase connections to the high voltage winding are any of these, then your phase shift matches the vector diagram. If it's any of these, then your phase sequence does not line up, it's reverse, and your phase shift will be the other direction. So instead of, in this case, dy1 lagging by 30 degrees, instead it would be converted to a dy11, and the low side would lead by 30 degrees. So it changes that phase shift. Okay. So this is really important. This is super, super important. You need to understand this. Uh, other, these were snips from a series of drawings for this transformer, and it does a better job of pointing out all of the different kind of components. Oh, one other thing that I wanted to point out is there's there's a common problem with people connecting the phases incorrectly to a transformer such that the phase shift is incorrect, right? This is why I emphasized this so much. But there's another way you can screw it up. If on your drawing you put the bushings in the wrong order, uh, that's going to that's also going to mess up your phase connections and it's not going to work correctly. So a common issue is when a drafter is drafting a drawing, say with two parallel transformers, and they want to copy one over to another spot instead of, you know, copying it and rotating it and moving it over. They might choose to mirror that transformer, and this happens with breakers a lot too. And if you mirror it, now it's like you've flipped the transformer upside down. There's no there's no orientation on this transformer where you could ever have the bushings H3, H2, H1 if the high voltage winding is towards the top of the page, right? The only way you could do that is if you actually, took it and flipped it over, right? If it's on the bottom of the page, obviously you could do H1, H2, H3. But if you rotate your transformer so the high voltage winding is at the top of the page, you will always find that the bushings are H1, H2, H3, and X1, X2, and X3. That's the way it'll always be. For a breaker, it's 1, 3, 5, 2, 4, 6. Um, it's not, I guess, super important for you to memorize that right here and right now. But I encourage you, when you start looking at this stuff, remember what I said and commit it to memory at some point, because it's super valuable to be able to do a quick sanity check and go, okay, well, is this oriented right? Because if you have the bushings in the wrong location and you start wiring up CTs that are associated with that bushing, but it's connected to the wrong phase, it's going to mess up your relaying. You're going to have misoperations, and it's not going to be good. So keep this in mind. It's a quick sanity check. You should always refer to the vendor's actual drawings to make sure that it's not different for some reason that I'm not considering or whatever. But like in any just about any case you can think of, this will be true. So think about that. Um, This is they're calling it the control box. It's also called a uh, control housing or mechanism housing or mechanical housing. There are a lot of names for it, but basically it's the control box where all of the controls for the transformer are. So this will have the LTC controls in it, the temperature controls in it, the if there's a nitrogen system, those alarms. Um, Basically all of the ancillary devices associated with the transformer will be in some sort of box on the side of the transformer. This is the conservator tank for this transformer. Here are the radiators, and this is a fan here. You got a couple of manholes to access the inside of the transformer if you need to. Here are some side views. These are the high voltage bushings here, low voltage bushings here. The X0 bushing is connected to the neutral of the transformer's Y winding. And then this is a copper bar that's coming down the side of the transformer and ending with a couple holes here that you can then tie this to the ground grid. So that would be your solid grounding connection. That's what it looks like. This is the control box here. This is the LTC compartment. The LTC compartment will actually have the current carrying components of the LTC. So like these taps and stuff will be in that LTC compartment. Trying to think, oh, what else? I guess that's it. Transformer nameplates are there. Okay. I guess that's all I wanted to talk about on the uh, not isometric, the section views of the transformer. This is an example of that no load tap changer position. So this thing's probably either screwed in or is lockable in that position, and you'd have to unlock it and then grab onto that handle and move it to some other position, and then re-secure it in that new location. So that's a picture of a no load tap changer handle. And then this is a picture of a load tap changer controller. So this, like I said, this is measuring the voltage somewhere on the low side of the transformer, and then these dials are setting like the bandwidth. So say you want to keep the uh, the voltage at your customers at 120 volts. So you can have a VT that's feeding this thing 120 volts, and it sets the band center at 120 volts, and then there's a bandwidth of, say 4 volts. So you can go down to 118 or up to 122, but if it gets outside of that area, this LTC controller will detect that and then automatically change the LTC position to keep it within that band. So that's I guess the theory behind that at a super high level. Um, this is the dial indicating the current position of the LTC. So you can see it goes from 16 lower to 16 raise. This is not this particular transformer. This is an old transformer I worked on for a project. It was actually we were replacing this LTC controller with a more modern controller. But you can see that the 16 lower and 16 raise was true for this transformer as well. That's pretty common. N here, this is the neutral position, and you can see this is currently at about 2 rays. And then these other pointers here are called the drag hands. And so let's say we hit the button that resets the drag hands. I think it's probably this thing here. This resets the drag hands. So there's a spring that returns both of these to the current LTC position. There's a little piton on each of them that when the LTC position changes, it pushes on that piton, and the drag hand moves with it. So say it goes from 2 rays to neutral, this would move with it, and this would stay right there at 2 rays. Okay, then it goes back to say 1 raise. Well, this one doesn't get pushed back. It stays right where it left. So this shows you the minimum tap and the maximum tap that the LTC has moved between since the last time it was reset. So this particular LTC looks like it operated between maybe 1 or 2 lower and about 5 raise, and neutral is within that area. So this seems like they did a pretty good job of setting the de-energized tap changer position such that the LTC operates around neutral. So, but that's how you'd tell. All right, so the primary focus, how long have I been recording? 45 minutes. Okay. The primary focus of this class is going to be the protection of three-phase power transformers. Most commonly, it's a single three-phase transformer in one tank. And there are instances where there's three single-phase transformers that are that have the windings made up outside of the transformer tank. Uh, that was done uh, much more commonly a while ago. Now they're almost all in the same tank. It's more efficient that way. They're cheaper. Um, there is an instance where you may run into single phase transformers that are newer, other than like if they're just trying to uh, replace something that has been in service for a while, and that's at like really big power transformer ranges. So I was reading an article about a transformer. I think it was in China. And it was like 2.1 giga MVA, and or giga MVA, giga VA, and the transformers were absolutely enormous, and there were three of them, and each was single phase, and then they were going to make up the winding connections outside of the transformer tanks. Uh, and there's, I guess, a couple main reasons why you would do this. First is just the physical size. You build the thing, and then you got to get it to where it's going to go. And there are uh, a surprisingly big number of logistical considerations that go into getting a very large transformer onto site. So say you've got it at a manufacturing facility, and then you got to load it onto a barge or a train and get it there, and then eventually, that's not right where they're building the substation, so they're going to have to transport it over the road. There are bridges, other clearance concerns, traffic, you know, um, the angles around turns, what have you, right? Tilt in the road, all kinds of different considerations for physically transporting it. So you can imagine if that each of these massive single phase transformers were going to be combined into one three-phase transformer, the sheer size of it would make it impractical to actually use. The other reason for transformers of that size to be single phase is for redundancy, because you have a transformer that size, it's probably pretty important to your system. What you can do is put four of them together and connect three of them with your transformer winding configuration taps made up outside of the transformer tank. And then if one fails, then you can reconfigure those taps, whether it's reattaching new bus work, or maybe it's already connected and you just have to close some switches in to try and swap it out. But you can bring in that other single phase transformer and replace the one that's missing, and then you can start transmitting power again. So or maybe you have to take one out for maintenance. You can maintain them one at a time without having very prolonged outages for the transformer. So those are the two big reasons why you might see those in large power transmission applications. But in general, it's going to be something like this. This is a three-legged core. You might also see a four-legged core, which basically just adds one more leg to the transformer, and that allows the zero sequence flux to flow. But most commonly, you'll see the three-legged core. Those are cheaper because you don't need the extra piece of core over here. So those are pretty common. They're smaller. This particular transformer, you can see, is a YY connected winding transformer. So the high voltage winding, H1 winding is here, and then all three of the non-polarity sides of those windings are connected together, and those go to the H0 bushing, and then the same thing for the X windings. Um, the vector diagram, I guess we'll discuss this briefly again. In three-phase transformers, the phase angle may shift from one side to the other. This is a an unavoidable property of delta Y transformers. The convention of the direction of rotation of the voltage phasors in the transformer is always counterclockwise, and then you have a 12-hour clock indicator, which is used to indicate the phase shift. So again, this is a DYN1 transformer vector diagram, and you can see that this matches that other nameplate I showed you. So even though it didn't say DYN1, we were able to determine that based on the vector diagram. This one's actually labeled. This paragraph is talking about that that phase sequence that we discussed earlier. So re-review this if you need to. So I wanted to give a real world example of a situation I ran into during my career where this came into play. So this is, or these are a couple of pictures from a small municipality that was having some issues with their system, and I got involved to do an event analysis for a fault that they had misoperated for. And me and Bill Wise, my coworker, went there and started looking at their system, and they didn't have the primary phases marked in their substation. There was a lack of actual PNC drawings at the substation, so we were like hand over handing circuits and trying to figure out what was going on. And we came up with a bunch of recommendations for them to correct the misoperations that they had been having ever since the substation had been built, which had been like 10 years prior at the time. And they agreed with all of the recommendations and they were excited to implement them. And so we were working with them to come up with an outage sequence plan so that they could take their substation out of service, make the changes while minimizing the impact to their customers. And they said that they actually had a tie switch that tied their 34 kV system, which is here, the 34 kV system, over to a local utility. And I said, well, that's great. We can just close that switch and then open these breakers and take your transformers out of service and do our changes, and then we can close everything back in, close the switch, and switch back over to, or open the switch back up and switch back over to the municipality's power. And they said, no, that we can't use that switch because it doesn't phase. And so I was thinking that maybe there was just some sort of rotation issue at the phase. They had brought in 1, 2, 3, and then 1, 3, 2 at the switch. So you can't close it because you tie 2 and 3 together on those two blades. And so you'd have to like roll this here, and now it'll phase and everything will be fine. So I said, well, can we change that rotation? And they said, no, it's weird. The phase tracker doesn't know what to do with it. We can't figure out why it doesn't work. And I said, I know what the problem is. So it turns out the phase shift for this transformer didn't match the phase shift for the local utility. So this, I guess, really emphasizes a point I was trying to make, is that you've got to be paying attention to this, not only at the local substation, because these two transformers paralleled just fine because they had the same phase shift, but they couldn't parallel to this other transformer that was remote to this facility and actually only was tied in some of the time for an emergency backup situation, but they couldn't close it in while both sides were energized because they had the wrong phase shift. So the two 34 kV lines were 60 degrees out of phase. So it didn't work. So what me and Bill did, we went to the closest utility substation because we could see the phases. They had their phases marked and we could see them from the road. So we took a picture and then we walked the transmission line to the municipality. It was miles long, but we wanted to make sure that there were no weird taps or anything that changed the phases between there and that substation. And then we traced it through to the H1, H2, and H3 bushings of the transformers and found that, yes, in fact, there were two swapped phases, and they were both, well, they were all DY1 transformers, so the 34 kV was 60 degrees out of phase, and thus the reason they couldn't use that switch. So we added that to the list of things to fix during this outage. The other thing I wanted to point out here is you can see we swapped these two phases on the high side, and then we also swapped two phases on the low side. And I quizzed the class last year, and Paul said he didn't even know the answer, which so I wanted to bring it up because I think it's going to be helpful. You guys know from having classes with Paul that if you swap two phases, you change the phase rotation, right, for the system. So if we had just swapped two phases on the high side, it would have changed the phase shift through the transformer, which is what we wanted. It wouldn't change the system rotation on the 115 side, but it would change it on the 34 side for the customers. It'd still be 1, 2, 3, but the customers would have two phases swapped. So they had three-phase customers that had motor loads and things. So if we hadn't swapped the phases on the low side, it would have made the motors run backwards, which would have obviously been bad. So we had to change them on the high side to change the phase shift, and then we had to change them back on the low side to have the same rotation at the customers. So that's what we did. This was the physical tap connections that they made during the outage. And then they changed these. This is the 34 kV structure leaving the station. This is the 115 kV bus bay structure. So you want to be the person that finds this issue and not the person that causes this issue. So pay really good attention to the phasing diagrams for transformers, how the phases are connected. It's super important. I don't know how many more times I'll need to say it, but it happens. It happens in real life. This is an example of it. It happens all the time, and I don't want you guys to be the ones that are making this kind of mistake. So, let's see. I've been speaking for just about an hour. I've got a ways to go. 33. All right, I got 10 more slides. I'm going to go through these pretty quickly. This is the part that I think is going to be review for hopefully all of you. So we're going to spin through this quickly. These are the different winding configurations. The reason that we have the 12 positions on the clock for like the DY1, DY11 vector diagrams, the reason we have the 12 positions is obviously the clock is 360 degrees, divided by 12 is 30 degrees per o'clock, say. And while the most common are 1 and 11, you can actually achieve any of those different clock position phase shifts through a transformer. You don't really need to worry about them, but I just wanted to make it known to you that it is possible. And here are the different ways that you can connect those windings to achieve the different phase shifts. So these are the Y connections and then the delta connections that you can use to achieve different phase shifts. The Y windings are almost always going to be Y0. This is like the simplest and most intuitive Y winding you can conceive of, and that's what is typically used. And then generally the delta will be either 1 or 11, as we talked about. Oh, this was something I want to talk about, the DAB versus DAC. So this is another type of nomenclature you'll see. What that means is, we zoom in on a D1 phase shift. If we assume that we connect the H1, H2, and H3 bushings to A, B, and C, then the polarity of the A bushing is connected to the non-polarity of the B bushing. You see that? So here's A, this is the polarity, and this this winding is connected B to A, right? B is the polarity, and the non-polarity is A. So this is how I think of it. It's a delta winding with the polarity of A connected to the non-polarity of B. Okay, so it's a DAB transformer, and that correlates to a DY1 transformer. The other way you could connect this, and actually I guess it's shown below. I'll move this here just so you can compare, right? So in this one, the polarity of A was connected to the non-polarity of B. Here, the polarity of A is connected to the non-polarity of C, right? So this would be a DAC transformer. That one over there would be DAC, and that is a DY11 transformer. So you can actually tell back in that nameplate drawing that we had, this one here, we could actually tell that this is a DY1 transformer without even looking at the vector diagram. And the way we can tell that is the H1 bushing, right? This is the polarity of A, okay? That would be connected, here's the F1 winding or whatever, that would be connected to the non-polarity of H2, right? It's kind of, I don't know if I'm explaining that quite well, but here's the polarity, right? F1 to S1 is this, so this is the polarity side. So here's the polarity side of H2. So the non-polarity side of H2 is here. So this is DAB. DAB is a DY1 transformer. So the vector diagram should look like that. So that's another way to tell if your particular transformer doesn't have a vector diagram on it, but it does show the windings, you can tell from that. And that's all explained here. I'm running out of time, so I'm trying to go fast. There, based on all of these properties, there are basically 4 types of transformers that you'll have to deal with, and those are YY, and the neutrals of each winding can either be grounded or ungrounded. Then there's Y delta, and this is in the convention of like the winding that's connected to the high voltage side is listed first. So YY, Y delta, delta Y, or delta delta. I've provided all of the data, all the equations that I think are relevant. So I apologize, first of all, because I made these while I was doing the research, not the research, but I guess you'd call it research, the preparation for these classes last year. There are a lot of examples of different transformer winding drawings and the equations that are provided with them, and I didn't find any that I really liked, so I ended up making my own. So I apologize if there's like a typo or something, but I did these myself in CAD. So this is what I think is the most important information that I find the most practical in my day-to-day career. So I encourage you to review these. Again, it should be all review. Um, and I'm missing a whole class worth of stuff to be able to go over this, so I apologize, but look through this. The key point that I do want to talk about is why you use one winding configuration versus another. The first winding configuration is the YY, and the YY transformer actually has two serious problems. And the first is if the transformer loads are unbalanced, then the voltages on the phases of the transformer can become severely unbalanced. The other one is the issue with third harmonics. So if the transformer is a normal balanced load, all of the individual phase currents are 120 degrees out of phase, obviously. But the third harmonics, because they repeat 3 times every primary cycle, they're actually in phase, and they actually tend to build up, and so those voltages, those third harmonic voltages, could get excessively high, and that's a real problem. So you don't usually see a YY transformer that's ungrounded on both sides unless you do one of two things to solve that problem. The first is to solidly ground at least one of the transformer Y winding neutrals. Okay. And this allows the neutral connection to basically let those third harmonic voltages dissipate through that connection. The other option is to add a delta tertiary winding to the transformer so that it's a 3-winding transformer. It's got a Y winding high voltage side, and then a Y winding low voltage side, and then a delta tertiary. And the delta has the same tendency. It allows the third harmonics to circulate in the delta and to dissipate and not cause those excessive third harmonic voltages. The delta tertiary also has the added benefit of providing a ground source. So one of the things, I try to be very careful with my language when it comes to whether or not a transformer is a zero sequence path or a zero sequence source. And those are very different. And we'll get into that when we look at the zero sequence impedance diagrams. So one or the other of these correction methods must be used anytime a YY transformer is installed. Then we have Y delta and delta Y transformers. Okay, I'm not going to cover both of them individually, but basically the delta Y transformer is the all-star of transformers. So it doesn't have any of the third harmonic issues. It provides a source of zero sequence fault current and not a path. And we'll talk about that on the other slide. I don't want to waste time. So those are good properties. The one downside of the delta Y transformer is that it's got a phase shift that you have to worry about. But now that you guys have had this class, you know all about it, and you're gonna nail it every time, and you don't have to worry about it. And if you don't have to worry about that, delta Y transformers are great. 90% of the transformers you work with during the course of your career will likely be delta Y transformers. And then delta delta is also an option. They don't have issues with third harmonics, but they have no ground source. My understanding is that they're using them a little bit more commonly with distributed generation now, but I've never actually worked on a project that had a delta delta transformer. So I guess that's about it on delta delta transformers. I guess we don't have the time to spend discussing further. So then we have the transformer electrical characteristics. So this is the zero sequence diagrams that I was talking about. So for a YY transformer, if it's grounded on both sides, there is a path for the zero sequence fault current to flow through. You can have a zero sequence fault current flow from the H bushings to the X bushings through the zero sequence impedance of the transformer. Okay, this is just the neutral of the return path. So there's a path through the transformer. If the Y winding is only grounded on one side, there is no path for the zero sequence fault current to flow through the transformer. It has to be grounded on both sides for it to flow through. Okay, and if it's ungrounded on either side, obviously it's open. So YY is pretty easy to understand the positive sequence and zero sequence impedance diagrams. Then we have delta Y. So let's do the delta Y instead of the Y delta first. But the zero sequence diagram, so because the high voltage winding is a delta, there is no zero sequence fault current flowing into the delta winding. But on the X winding, there's actually a path for the fault current to return to ground. So this is actually a source of zero sequence fault current, right? So here it's not a source, it's just a path for it to flow through, right? So uh, there's no isolation between zero sequence faults on the high side and low side of the transformer. Whereas here, there is isolation between the high side and low side, and also it is a source of ground fault current. So those are very handy properties. And then I'll demonstrate that in Aspen one-liner really quickly. So if we have, let's say, this delta Y transformer here, we have a single line to ground fault on the low side of the transformer. You can see this is looking at the zero sequence current. There is essentially no zero sequence current coming out of the delta, right? If we put a fault current on a single line of ground fault on the high side, you can see that there's actually 7,200 amps coming out of this transformer, even though this generator is offline. So this is just coming from the transformer itself. The transformer is a source of zero sequence fault current. Okay. This is how like a grounding transformer works too, right? It's just energized from one side and yet it still provides zero sequence fault current. Okay. Meanwhile, if we have a YY transformer where this is grounded on both sides, I take all this stuff out just to make it simpler. This is just a path through which the ground fault current flows, right? So this ratio here is just the inverse of the transformer ratio. So this fault current is not being sourced from the transformer. It's just flowing through from the high side. Okay. If we put this back in, you can see no zero sequence fault current is flowing into the delta, obviously, because it can't flow into the delta, but it is flowing out of the Y. Here, it's flowing into the Y and out of the Y, but it's just flowing through the transformer, not being sourced by it. Okay. And then I guess if we make, let's say the high side is ungrounded. Let's just put in a bunch of nines here. Now we do a zero sequence fault current, zero sequence fault rather, and there's no fault current flowing through the transformer. Even though one side is solidly grounded, it doesn't flow through because the other side is ungrounded. Okay, I am out of time. I managed to get through everything I wanted to, although not in the depth that I wanted to. But we made it. So next time we'll pick up on types of transformer failures, and then we'll start getting into protecting transformers. Okay, thanks everyone. Have a great evening.